Welcome. Continuity is going to be the topic of today's lesson. And in fact, we've been using continuity for a long time. Since the first lesson, we started substituting the numbers into our limits, and we can do it only when the function is continuous at the point. So in fact, we use continuity, but we never actually touched the definition of continuity, and today was going to happen. So we already know that function is continuous when we can draw it, sketch it, without lifting your pencil, chalk or something. Yeah, sure, this is kind of simple definition. Right, now we'll give a strict definition. So your function f of x is gonna be called continuous at point x, at point A, right? If three things happen, three things are true. First, your function is defined at point A. So that's why we shouldn't even write it down. This way it's going to be f of a. So your function f of a is defined, right? It exists. Defined. And it's equal to something. F of a exists, defined, and exists. So you understand. So there's just some number. F of a, it's number. So there's no such thing as you substitute a's here and you get undefined. So it's going to be the end, right? It's not continuous for 100%. Second important thing. Limit as x approaches a of f of x exists. So this is second super important condition. It should exist. This limit must exist. And basically, how do we check it? It just means that the left-hand limit should be equal to the right-hand limit. So this is what we want to check. And if they're equal, then yeah, limit exists. All right, and third, the final thing is that, yeah, indeed, then the limit as x approaches a of f of x is going to be equal to f of a. So basically, this is what we used already, right? So we substitute, in fact, just the number in the function, and we say, okay, this is f of a. Yeah, so it works every time when the function is continuous. And you have two preconditions, right, before you use this one. So if these three things are true, then your function is called continuous. Very easy. Yeah, three super important conditions. So then we'll be able to call your function continuous. And of course, all the basic, let's say, elementary functions, they are continuous. Polynomials, think about polynomials. They have no strange points, right? No. Of course, I know you take any polynomial, you will literally, and of course, if you talk about graphically, right, about this graphically, then yeah, as I've already discussed, continuous function is function which can be drawn, sketched without lifting a pencil. So there's no breaks, holes, jumps, or something. Now we'll actually discuss the types of discontinuity, but this is the point. Now we take the graph, boom, 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 no, nothing strange, right? It's basic graph. Yes, of course, it's kind of strange. Graph in and of itself is strange, but there's no breaks, holes, or jumps, or something. At least it's fine, right? It's fine. So it means continuity. It's continuous. What else do we want? And in fact, so as I told you, polynomials, right, they are all continuous, of course. What else? Trigonometric functions, all those functions, they are all continuous. Trigonometric, logarithmic, exponential, all the functions, polynomials, rationals too, provided, of course, that if you have a rational, f of x divided by g of x, right, this is a rational, some rational function. Of course, provided that at point C, imagine, okay, point A, it's not zero, right? For all points except this one, it's also going to be rationals also continuous. So basically, most elementary functions, they are all continuous. This is it. What else now? Let's actually discuss now types of discontinuity. So first type of discontinuity is going to be, let's even look, let's show it here. It's called removable discontinuity. Yeah, let's start with removable discontinuity. And here's why. Removable discontinuity, in a simple language, means hole. So when you have a hole in your function, you just move, and you have a hole. Oh, hole. Why do we call it removable? Because usually, what's the hole? It's, for example, we have a function. I know. Let's say that f of x. This is our function f of x, and f of x looks like what? It's kind of now, I don't know, x to the fourth plus 3x squared minus 7x plus 3, something like this, right? So we have some polynomial which is continuous in and of itself. But how do we get a whole? Where does it come from? It just, because usually it's just some piecewise functions where we say, for example, it's for all x, okay, we won't use these brackets, we'll just say for all x not equal to some unknown, maybe 2, right? For all x not equal to 2. So it's true, but at x equal 2, it's undefined. Function is undefined. So in this case, you have a whole. Yeah, you get a whole, and when you have a whole, it means that your function is undefined. And we look back at the continuity conditions, right? Then the first condition is not completed, right? So it's undefined. Basically, we stop here. Of course, it's not continuous then. So this is basic type of discontinuity. And the reason we call it removable discontinuity, so simply, of course, that's a whole, right? Yeah, that's a whole, literally whole. But we call it removable discontinuity because it's easy to remove it, literally, because you just have to redefine the function. You have to return back normal polynomial. What are you doing? Yeah, just remove this x not equal to 2. Just do it this way, and that's the end of your problem. Your function is continuous, no holes, nothing. Yeah, and the life is great. So this is your function, no holes, and life is great. That's why it's called removable. So remember, whole is basically removable because it's literally easy to remove the whole if you do some normal stuff, right? If you just take and remove some weird things like this is not equal to these or these, and that's all. So this way you can remove the discontinuity when you have a whole. This was the first type. The second type is, let's keep it, okay? So let's call it, this is the first, I already wrote, it's going to be removable discontinuity. Removable. Second one. We don't have too much place, unfortunately. Let's do it here. Removable, this is first. Second, jump discontinuity. And as you understand from the name, it's going to be jump. Usually it can be something like this, and then a jump. I don't know. So there's literally a jump, a gap. Right, when you go, so you have a normal function, boom, jump, gap, some empty space. What's that? Again, that's weird, absolutely weird, all right? So you see that and you say, yes, absolutely, our function is going to be not continuous. And why? Okay, it's defined, basically, right? So if this is the point A, let's say it's A, our function defined, in fact, right? So we have some value at point A. So it's here, our function is defined, yeah, then we go, yeah, there's some jump and we go further, go to the top, move to the top. But it's defined, in fact, it's defined, right? We see that there is a value at point A. So it's, actually the first one is true. We move forward, we see the second one. And the question is, does our limit exist? And the question, and the answer is, of course, not. Because what's the left-hand limit, right? We approach from the left this value. From the right, we approach this value. Of course, they won't be equal. So the left-hand limit is not equal to the right-hand limit because they approach different values from the right and from the left. So the general limit doesn't exist. So the second condition fails. And this is the end, right? So it's not continuous. That's why the jump discontinuity, so there's such thing as jump discontinuity, right? So this is the second type, jumps, gaps, as you wish. And the third one, also a very interesting one, asymptotes, vertical asymptotes. So let's write down as vertical. Vertical asymptotes. So, vertical asymptotes. What's that? Unfortunately, I don't have too much place. I'm sorry, I will have to remove these three conditions. I hope you already remember them. Of course, very easy. Yeah. They're very simple. So, vertical asymptotes. This is the third situation. And yeah, we just have to remember our favorite function 1 over x. And if you look at the point 0, what's happening here? Is it continuous? Our function is super strange. It's first, a bunch of conditions fails at that point. So let's look at point x equals 0. Does our function f of x, which is 1 over x, continues at point 0? Of course not. First, it's undefined at point 0 because it's going to be 1 over 0. So it's undefined first. First condition fails. Second, the limit also doesn't exist, right? From the left, we approach different, from the left and from the right, we approach different values. So the second condition also fails. So for 100% vertical asymptotes, there are also cases of discontinuity. That's why absolutely, yeah, it also fails when we have a vertical asymptote. Imagine we have one. Now imagine we take now we take 1 over x squared, right? Anyway, nothing changes. It's undefined. Yeah, the limit in fact exists, maybe, but infinite limit, right? This is already weird. But it's undefined, so it's discontinuous. Any vertical asymptote, remember, any vertical asymptote, it means that your function is not continuous at the point if you have vertical asymptote. So 3 different situations: Hall, jumps, and vertical asymptotes. 3 different situations. In all these 3 cases, your function is going to be not continuous. Okay, very simple. Now let's practice a bit. Yeah, let's solve some problems. All right, so when we talk about continuity at a point, that's very easy. You just need these 3 properties, 3 conditions to be true. Right? First, your function should be defined there. Second, the limit should exist. And 3, the limit, right, must be equal to that to the value of your function at that point. So simple. This is how we define the continuity at a point. So what do we do when we're having an interval, right? So we say that is very easy. We say that f of x is continuous on the open interval if it's continuous at every point. Very simple, right? So on the open interval, we'll say that function f of x is continuous on this open interval if it's continuous at every point of that interval. Very simple. And we also say that it can be continuous. We say that it's going to be continuous on the closed interval if it's continuous at every point of this interval. Plus, if you talk about endpoints, there's a bit different thing, and it also should be continuous from the left at the left endpoint, and it also should be continuous from the right at the right endpoint. So this is not A, B, right? So if you have an open interval, then everything is very simple. It's going to be continuous on the entire open interval if it's continuous at every point. If you have a closed interval, then you also have to add these 2 things, that it should be continuous at every point of the open interval plus these 2 limits, right? It should be continuous from the left, let's say. This limit from the left should exist at point f of a, and it should be continuous from the right at the right endpoint, right? At the left endpoint should be continuous from the left, and at the right endpoint should be continuous from the right. And this is it. So basically, you add these 2 conditions there. And this way we can define the continuity on an open interval and on a closed interval too. And that's why now we can actually say that, yeah, elementary functions, usually they they are continuous at the entire domain. So you just take the domain, usually, so every elementary function, every logarithmic, trigonometric, every function you find the domain. Right, for example, let's look at the rational function. I don't know, again, so 4x cubed plus 2x squared plus 1 divided by 4x to the fourth plus 7x plus 3. It doesn't matter. Oh no, let's take different one. I don't like this. Let's take easier. Just take x squared plus 2x plus 1. Beautiful. And you look at that, and you just have to define the domain. First, you find the domain. For example, imagine I want you to find the continuity, right? To define the continuity where it's continuous, where it's not continuous, for the entire, for all real numbers, right? I just want to define the continuity. Imagine I want to find the continuity of this function. And all you have to do when you have an elementary function, exponential, logarithmic, any function, you just find the domain first. You find the domain, and then that's going to be the interval where your function is continuous too. So what's our domain here? Basically, that's just 4x cubed plus 2x squared plus 1, all right, divided by x plus 1 squared. So we know that x cannot be equal to -1. So the domain of this function is from negative infinity to -1, and then from -1 to positive infinity. Right. So this is the domain of our function, and for all values inside, so on this interval, right, our function is continuous too. And this way you work with any functions, right? You find the domain, and you will be fine then. You find the domain, you see where it's not continuous, then it will work. You see when it's not defined, and so it's not going to be continuous there either. All right. So just a few words, but in fact, yeah, it's of course that's super clear. One more thing to note. There are actually 4 theorems of continuity. So when you have a function, I guess let's remove this. And then, yeah, I promise you, then we'll start practicing continuity. But it's not hard at all. Basically, we already discussed everything you need to be a master of continuity. So there are 4 theorems that say that if you have a function f of x and g of x, so let's start with first 3 theorems. So you have 2 functions, and for example, they are both continuous at point C. Then the difference and sum of these 2 functions, right? Imagine you want to add up these functions or you want to subtract them. Anyway, eventually you will get a, so if you look at these functions if you look at that as the entire, like as a whole, as a function, that's going to be a continuous function too. So the sum of continuous functions is going to be continuous function. The difference of 2 continuous functions is going to be a continuous function. The product of continuous function is going to be a continuous function. The quotient of continuous function is going to be continuous function, provided that, of course, g of c is not equal to 0. That's all. So again, if you have 2 functions, f of x, g of x, and they're continuous at point C, then the sum of these 2 functions, or difference, will give us the continuous function. The product will give us continuous function. The quotient also is going to be the continuous function if, of course, provided that g of c is not equal to 0. And there's also a theorem about composite functions. So if, let's say, g of x is continuous at point C, right, first, and f of x is continuous at point g of c, so g of x is continuous at point C, and f of x is continuous at point g of c, right? It's going to be a composite function. Then the composite function, or f of g of x, also is going to be a continuous function. Very simple. So if it's continuous, it will be continuous. If they are both continuous, it will be continuous. The same thing here. So it's 4 theorems. That's basic theorems that work everywhere, right? Everything we introduce, limits, the same thing will happen with derivatives. We'll kind of touch the composite functions, the sums, the differences, products, and so on. But basically, of course, they are very true. Imagine you have a function where no breaks, no holes, no vertical asymptotes, and you add them up, right? Or you, for example, you subtract one from another. Of course, nothing changes. There's no hole now from nothing, right? It can just appear. It can just occur. You can't just add up some functions and then it turns out there's a hole now, or break, or something. No, it doesn't happen this way. So, of course, if you add up some difference of continuous function is going to be continuous function. If you multiply them, of course, again, nothing's going to change. It will be continuous function. And so on. So, yes, very simple, very simple. Now that's all. So now let's solve. I can't even say solve. Now let's consider different functions and say what is the continuity, where is discontinuous, what is the type of discontinuity there, and so on. Maybe we'll determine the domains, right? Not only the domains, where it's continuous, whether it's continuous on the interval, maybe some interval or something. Yeah, so let's start with the first one. Maybe let's change the color. Let's add some colors to our life. So let's start with the first one. Okay, let's say we have a function f of x, which is -1 for all x less than or equal to 0, and it's going to be 3x squared for all x greater than 0. All right, again, we can do it. We can tackle this problem in a couple of ways. In fact, we can look at that graphically. We look at the graph, and let's actually do both. We look at the graph, and we see that for all x less than or equal to 0, it's going to be -1. So something like this, right? Then it's suddenly a parabola that goes from 0, right? It grows, so if you substitute it will be 0. So we have a jump. We'll already see there's going to be a jump and some parabola. So this is our graph, the graph of our function. And what do we see? We see a jump, definitely. It was -1 and then it jumped to 0. So, of course, this is going to be jump discontinuity. And we also, of course, if we look at the first condition, then f of 0, right? So I'm interested in continuity at point 0, right? I want to find the continuity at point 0. So analytically, you look at f of 0. You see that it's defined, in fact. F of 0 is defined, and that's -1, right? So first point is fine. First condition works. It's actually 0. It's actually -1. So the value exists. The function is defined. Second, this is where it fails, right? The limit doesn't exist, unfortunately, as x approaches 0 of f of x. D and A doesn't exist. And yeah, we see that because from the left we approach -1. The left-hand limit will be equal to -1. The right-hand limit is equal to 0. So they're not equal. The limit doesn't exist. So this is the end. Analytically, both analytically, graphically you just recognize the jump. Analytically, you see that the second condition fails, and of course it's not continuous then too. All right, next function. Let's look at 1 over x minus 3 squared. So, and I wanna see the continuity. Okay, if I ask you about the continuity at any other point, by the word, is it continuous at any other point? Yes, absolutely, absolutely. If you look at the function, so in fact, it's continuous on the entire domain, except for this point. It's the only point of discontinuity on the entire domain of this function. For any other point, yeah, it's true, it's continuous. You take any other point, it's going to be continuous. At point 0 is discontinuous. All right, now we look at this function. We move to f of x, which is 1 over x minus 3 squared. And what do? We do a graph. Let's start with the graph first. So what's that? At point 3, as you see, at point 3 we'll have a vertical asymptote. And actually, maybe you don't see, but so how do we recognize whether we'll have a vertical asymptote at some point or not? That's very simple. You have to think about it as the limit. Imagine you take the limit from the right. You look at the limit from the right. Okay, you imagine. So I'm going to evaluate the limit from the right at point 3. Again, so I start with point 3. I'm interested at point 3. I want to know the continuity at this point. So I look at the limit. Let's start with just right-hand limit, let's say. As x approaches 3 from the right, I just think about it. So what's happening here is going to be 1 over x minus 3 squared, right? So if you substitute 3, we get 1 over 0. And it's kind of 1. So imagine dividing 1 by something super small. So it's not actually 0. It's something really small. So even if you add, for example, if you even if you divide 1 by 0.001, right, you will get 1,000. True? True. If you divide by 0.00000.1, you will get a million, and so on. Now imagine we get really super infinitely close to 3. So it will be 1.00010, right? So the number will be super huge. So yeah, it's going to be infinity. So this way, thinking about the function this way, about the limit this way, you can recognize the vertical asymptote, because it means that it grows without any bound when it comes to 0 from the right. From the left, the same thing. Because of course, if we remove squared, right, then it will be positive infinity, because we'll have some positive, that will have some 3.00001, right? So we get 0.001, it's positive, so we get positive infinity. But if we go to 3 from the left, if we approach 3 from the left, we will have some number which is close to 3 but less than 3 still. So we will get a negative infinity, but here we have a squared, so we don't care. We get a positive infinity anyway. All right, so by the word this way, we can recognize that, yeah, sure, there will be some vertical asymptote. And yeah, I know that the graph will be, so at point 3, we have a vertical asymptote. So if we substitute 0, it will be 1/3, right? Something like this. And something like this. So yeah, 3. Again, so this type of line, right, x equals 3, is called vertical asymptote. Absolutely, 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 absolutely. Okay, so what else? We see, of course, so now we basically solved the question of the continuity too, right? So we know that this vertical asymptote, it's the third type of discontinuity. Yeah, sure, it's discontinuous at point 3. But if we look at the other points, yeah, it will be continuous. It will be continuous. So this is the type of vertical asymptote, right? It's also a type of discontinuity, vertical asymptote. And let's also bring some third discontinuity. Which one? Whole. This is extremely easy. Yeah, we just need some function which is undefined. We can even look at this function, and this function can be a discontinuous function if we say that x is not equal to 1. Then at this function, at this point, at point 1, it will be undefined. At this point, it's undefined, and it means, if it's undefined, that at point 1, it's also going to be not continuous. Very simple. Or actually, yeah, I actually recalled very, very popular example. Yeah, people really love this type of functions. F of x, x minus 1 squared, let's say, divide by x plus 1. So imagine we look at this function. And this function, we know that this function, okay, there's nothing else. So this is just our function. And we know that, of course, x cannot be equal to -1, right? If it's -1, then the function is undefined. So it doesn't work this way. So x is not equal to -1. And this is going to be our point of where we'll have a hole of our removable discontinuity. So if you look at the function, in fact, it's gonna be, in fact, this is our function. But at point -1, it's undefined. Now, wait a second. Yes. So if we, so what's that? That's x -1, x plus 1. We divide, we cancel x plus 1, we get x minus 1. We basically get 0.0, it's -1. Yeah, it's kind of true. So -1, and it's x is not equal to -1. Okay, so at point -1, at this point, we have a hole. So here we have a hole. Here our function is undefined, and unfortunately, there the first condition fails, right? Our function is undefined there. So for this function, it's discontinuous at point, it's not continuous at point -1. But on the entire domain, except for this function, it's continuous. And by the word, actually, imagine I just redefine the function. It's removable discontinuity, right? It's removable discontinuity. So maybe I just redefine the function. What if I redefine the function this way? So now my function f of x is going to be x minus 1 over x plus 1 for all x not equal to 1. And I will redefine the function. I will say that at point -1, when x is -1, it's going to be equal to 3. So my graph now will have a, still it will have what? Well, it will have a hole here, but at point 3, sorry that let's maybe remove, let's move graph here. So my function defined this way, and so now at point -1, I say that it's going to be 3. So this is our function, right? At this point we have a hole, and we move forward. But I said that at point -1, now my function is equal to 3. I know, so it's here. So it's actually defined. The first thing doesn't fail. It's defined. Then, so first, let's remove that, right? We go step by step. Let's actually discuss discontinuity in this case. Such an ugly desk, sorry. So, it's our function. And at point, first, at point -1, so this is -1, we look at discontinuity at -1. At point -1, function indeed is defined, but it's equal to 3. So this is how we redefined our function. So basically, first one works, right? It's true. Second, does the limit exist? Yes, absolutely. From the left we approach, what is the value we approach from the left? X plus 1. We approach, now I will say, wait a second. We approach 2. Yeah, from the left we approach 2. -2. From the left we approach -2. From the right, so left hand limit as x approaches -1. Now we will actually show that of x minus 1 squared over x plus 1 is equal to x minus 1 multiplied by x plus 1 divided by x plus 1, right? So we cancel out x plus 1, and we get the limit as x approaches -1 of x minus 1. So it will be -2. And we know that it's equal to the right-hand limit. So it's equal to the limit as x approaches 1 from the right. They're equal. So the left-hand limit and right-hand limit are equal. And we see that. I mean, we approach the same value from the right and from the left and from the right. We know that. We see it. Yes, it's true. So already 2 points are true. 2 conditions are true. And now the third one. But this one, final condition, doesn't work. Because, so the limit, we know that limit, then general limit exists, right? The limit as x approaches 1 of x minus 1 squared over x plus 1 of this function of f of x. So I'm sorry, that's not our function, right? Our function is piecewise function now. The limit of f of x exists and it's equal to, as x approaches -1, right? We approach -1, exists and it's equal to -2. But the function, it's not equal to f of -1 because f of -1 is free. That's why, yeah, we kind of redefined the function, but it didn't help. Only if we said that at point -1 is going to be 1, if we redefine the function this way, only this way, it could help. And then if we did that, it would help and it would be continuous function. Actually, I guess that's all for continuous, but in fact, this is very easy. You just have to remember these 3 conditions and you will be fine. You'll be fine. All right, now let's talk about intermediate value theorem. And basically, it's kind of clear. It just says that if you have a function f of x, which is continuous on the closed interval a from a to b, right, on this closed interval, and it says you can take any number between f of a and f of b, right? You can take any number d, let's call it d, between f of a and f of b. So between values evaluated at endpoints, right? You can take any number d. And it says that guaranteed, there will be some c in open interval from a to b, which is, where your function evaluated at this point, at point c, will give you d. So if you have f of x, some function continues on closed interval from a to b, and you take any value between f of a and f of b, right? Take any value d. And then it just says, it's guaranteed, there's some c inside, right, in the open interval where f of c equals d. At which point, some point c where your function attains value d. So this is it. And it actually, it doesn't say how many points. There can be 2, 3, 4 c's, I don't know. But the main point is that at least one c, it guarantees that at least one c, there's just at least one c point where your function attains d. And it's kind of clear. So imagine any function, you take a function, right, on some interval. Yeah, of course, if you take any value of your function, right, so this is going to be d. Take any d. Yes, of course, there will be at least one c where your function attains this value, right? There will be c, guaranteed. If your function is continuous, guaranteed. If there is no holes, if there is no breaks, if there's no vertical asymptotes, there will be 100% will be point c, where f of c equals d. And it's kind of clear, of course. Yeah, sometimes, I mean, if your function, for example, is this, and imagine, so this is d. Yeah, and in fact, there are 2 points. And if you take this interval, so this is going to be a and this is b. In fact, there will be 2 points, c1, c2, right, where your function attains this value d. 2 points, there will be 3, 4, 5, I don't know, 6, any number. But the main point is we're guaranteed at least one. At least one is guaranteed. If you take, if d is some value between f of a and f of b, right? So this is it. That's why, of course, very simple. This is intermediate value theorem. And the last thing, I guess, let's just a bit. Of course, we already talked a lot about vertical asymptotes, about horizontal asymptotes, but let's just, again, every time when you have a function, f of x, right? And if it grows without any bound at point c, at some point c, right? So we have point c, and grows without any bound there at this point. Of course, it doesn't cross it. So this line, so line x equals c, we call this line x equals c, right? This line, this vertical line x equals c, we call it vertical asymptote. Yeah, in fact, this is just vertical line x equals c, where c is just a point where your function grows without any bound. So if you have a limit where x approaches c and your function f of x, from the right, from the left, maybe general limit exists, right? We already saw a lot of different situations. Maybe it approaches from the right, positive infinity. Maybe it approaches negative infinity from the left. I don't know. Maybe general infinity at infinite sense, it doesn't exist, right? Anyway, so if it approaches C, maybe from the right, from the left, maybe generally, right, and the limit exists and it's equal to some infinity, which means that your function just grows without any bound. At this point, C is going to be, so then the line x equals C is going to be vertical asymptote. This is the line, vertical line, which will never be crossed. There will be no intersections, so it will be never crossed. Okay. What else? What else? And also, as you remember, sometimes this is first case, yeah. When your function grows without any bound at some point, this is going to be the vertical asymptote. C is going to be vertical asymptote. And we also discussed the situation where x approaches infinity or negative infinity, right? So we will look at the values where x grows sufficiently, where x is really takes really high, really attains really huge values, where x is really huge. And in these situations, if you can see some pattern where your function gets close to some line, right? So one more example. Imagine, so your function, it kind of goes there to the right side, and you see that it's never, you find the limit, you take the limit, and you see that it gives you the finite number, some number, I don't know, 5. Right, it doesn't give you infinity. If it gives you infinity, it means that it also grows without any bound. So there is no bound; it just grows. As x approaches infinity, as you take large numbers of x, as you go far away, it also goes somewhere to the top or maybe downward. It depends on the sign. But if you get some finite number, 5, it just means that this is 5, right? And it never crosses the line y equals 5. And this is going to be horizontal asymptote, yeah? Vertical asymptote is then, so you have vertical asymptote every time when you approach some finite number, x approaches finite number, and your function grows without any bound. And the horizontal asymptote will be when your x approaches infinity, negative infinity, positive infinity, and you take the limit, and then it turns out it's going to be a finite number. It's just a number 5. Think about it. You grow x sufficiently without arbitrarily, right? It's like arbitrarily large, and you look at the function, and it somehow, I don't know why, it turns out that it somehow gets close to a finite number, so it doesn't grow without any bound. Maybe it decays, I don't know, but it actually gets close to some real number. So then y equals L, right, generally, but here it's 5, y equals L is going to be horizontal asymptote. X equals C is going to be, so if it's generally this is not 5L, some real finite number, y equals L is going to be horizontal asymptote. So this is line your graph never crosses, even when, and you know, now it's not, of course it can cross it here, but at point, it's, you know, sometimes you can see these type of functions. So in fact it crosses the line, but as x approaches infinity, at the very huge axis, it doesn't matter. So it will anyway, it's just like the behavior, right? It's a pattern of a behavior. So as x approaches infinity, it will get really, really close to L. Never touch L, of course. Never touch this line, but it will come close to that. And basically this is it, right? Because in fact, yeah, continuity, it's easy. The intermediate value theorem, when you understand what's continuity, is super obvious. Vertical asymptotes, horizontal asymptotes, we actually discussed them too. So right now, in fact, you know everything about limits and continuity. Of course, in units 1 smash time, we'll wrap up all the things we've covered here, and you'll learn a bunch of stuff. We'll practice a lot. But for now, yeah, practice yourself, of course. Solve the tests and maybe do some additional practice on your own. I don't know. But you have to practice, you see your mistakes, and then, of course, look at the unit 1 smash time. And you'll be pleased, I guarantee you. And after that, you'll be a master of limits and continuity. And this is going to be the foundation of your calculus knowledge. So, happy studying. See you soon. Smash AP.